Ever get that sinking feeling? You know, when you finally click update on some software, the one you've been putting off forever, and then, well, things just go haywire.
Yeah, I know that feeling.
It's like a constant battle against the tide of change in tech, and sometimes those changes feel more like a burden than, well, progress. It really reminds me of that old saying by Heraclitus, the only constant in life is change. It's incredibly true in the fast-paced world of software, wouldn't you say?
Absolutely. And that very idea of constant change is what brings us to today's deep dive. We're going to explore this fascinating concept. Maintainable code generation. It's like thinking ahead, building software that's not just ready for launch day, but also prepared for all the inevitable changes down the road.
Right, exactly. And to guide us, you've brought some really intriguing material, haven't you? We're delving into a research paper titled MaintainCoder, Maintainable Code Generation Under Dynamic Requirements. So are we peeking behind the curtain to see how AI is tackling this challenge of creating software that can actually roll with the punches, so to speak?
You got it. This paper presents MaintainCoder as a fresh approach to software development powered by AI, but with a crucial twist. Its main goal is to ensure that the code it generates is inherently easier to update and modify, especially as those pesky requirements change, which, let's face it, they always do. So our mission, should we choose to accept it, is to understand why this whole maintainability thing is so crucial, what the brilliant minds behind MaintainCoder did to make it happen, and what it could mean for the future of software development as a whole.
Okay, maintainable code generation. It seems pretty straightforward, doesn't it? I mean, why wouldn't we want software that's easy to maintain? But the very fact that this research exists tells us there's a real problem here. So let's break it down. Why is maintainability so essential in software development, and why do you think it's often overlooked in practice?
That's a great place to start. You see, at its core, maintainability is all about how efficiently, how cost-effectively we can adapt and modify software throughout its entire life. While everyone dreams of software that works perfectly from day one, the truth is, software is rarely ever static. Needs change, new features get requested, bugs pop up, and technology keeps evolving. If the original code isn't designed with future changes in mind, even the smallest tweaks can spiral into complex, expensive nightmares.
So give us some real-world examples to drive this point home. I mean, we've all experienced frustrating software, but what are some high-stakes situations where this lack of maintainability caused major problems?
Well, the paper highlights a couple of pretty striking examples. Remember the Knight Capital Group? They lost a staggering $440 million in minutes.
Yeah, I remember that. That was crazy.
And the culprit, you guessed it, problems in their legacy code.
The code that was poorly maintained.
Exactly. It seems like a small oversight, but it had massive financial repercussions. And then there's the infamous Y2K bug. Remember that one?
How could we forget?
The world spent an estimated $100 billion just to fix potential issues in outdated code. It's mind-boggling.
It is.
These examples really highlight how short-sighted coding decisions can snowball into exponentially larger costs down the line.
Yeah, those numbers really put things into perspective.
And it's not just these high-profile disasters. Studies show that a whopping 60 to 80% of the total cost of software over its entire lifespan comes after it's deployed.
Really? That much?
Yep. And most of that is due to maintenance things like fixing errors, adding new features, adapting to new technologies.
Makes sense.
And the root cause of these high maintenance costs is often poor design choices early on.
Like what kinds of things?
Think tightly coupled code, where everything's tangled together, not well organized. Even a small change can ripple through the whole system, leading to unexpected problems.
It's like that saying, for want of a nail, the shoe was lost.
Exactly. It can have a cascading effect.
I think we've all experienced apps or websites that feel like they're cobbled together with digital duct tape.
Oh, yeah.
Slow, clunky, hard to update, and you just know there are underlying code issues causing constant headaches. So if maintainability is this crucial and neglecting it is so costly, what's the typical approach to code generation, especially with AI in the mix? And where does it fall short when it comes to building software that can gracefully adapt?
Right, that's the crux of the problem. The paper points out that AI-driven code generation has gotten really good at creating code that's functionally correct, meaning it runs and passes the initial tests. Benchmarks like Human Evil have pushed the boundaries of getting AI to create code that does what it's supposed to based on a set of predefined test cases.
So it's like checking if the code produces the right output for a given input.
Exactly. But here's the catch. The static tests are just a snapshot in time. They don't really tell us how well that code will handle future changes and requirements.
So will it be easy to modify, or will adding a new feature break existing ones?
Precisely. Current code generation systems and the benchmarks used to evaluate them don't really focus on these dynamic aspects of software.
It's like testing a car on a perfect sunny day, but not seeing how it handles snow, ice, or the need for a new transmission down the road.
That's a great analogy. While some newer benchmarks are starting to consider things like readability and efficiency, they still rely heavily on those static evaluations. They don't stress test the code's ability to adapt and evolve over time. And that's where MaintainCoder and its accompanying benchmark, MaintainBench, come into play.
Ah, MaintainBench. Now things are getting really interesting. Tell us about this new benchmark. What sets it apart from the others, and how does it actually measure maintainability?
MaintainBench is quite innovative. It's the first benchmark specifically designed to assess code maintainability through what they call requirement evolution cycles.
Requirement evolution cycles.
Yeah. Instead of just checking if the code works for the initial problem, it tests how well that code can be modified when the requirements change.
So shifting the focus from just getting it right initially to ensuring it's built to last.
Precisely. They take those existing code generation benchmarks, like human eval, and give them a clever twist.
How so?
They introduce changes to the original problems and then see how easily and efficiently AI models can tweak their generated code to meet these new requirements.
Okay, that makes sense. But how do they do that practically? What kinds of changes do they throw at the code?
They've identified 4 main requirement change patterns. First, there's functional extensions, or PEXT. This means adding new features to the code while making sure the original functionality remains intact.
So like adding a new filter to a photo editing app.
Exactly. The core editing functions still have to work, but now there's this added capability. The second pattern is interface modifications, or PINT. This involves changing how the code interacts with other parts of the system, like modifying the input parameters of a function or altering the type of data it returns.
So if one part of a system gets updated, how well can this code adapt to the new way of interacting?
Right. Then we have data structure transformations, or brights.
Yeah.
This requires the code to adapt to different ways of organizing and storing data.
Like switching from a list to a dictionary.
Precisely. This can impact both the efficiency and the core logic of the code.
That sounds like it could require some pretty significant changes under the hood.
Definitely. And finally, there's error handling enhancements, or PER. This involves adding specific error handling mechanisms to the code to ensure it can handle unexpected situations gracefully.
Essential for real-world software, right? You don't want your app crashing every time there's a small hiccup.
Absolutely. To create these extended data sets with these new requirements, the researchers used a process they call solution test coevolution. They primarily relied on a powerful AI model, GPT-4o, to generate initial versions of the modified code and the corresponding updated test cases.
But just letting AI change the code and tests on its own seems risky. How did they ensure everything stayed correct and accurate?
They have a very thorough manual review process, 3 stages, in fact.
Okay, tell me more.
First, they review the AI-generated problem descriptions, making sure they accurately reflect the intended changes. Then, programming experts meticulously correct any issues, ensuring everything aligns perfectly. And finally, a separate team does cross-validation to independently check that the original functionality still works, the new requirements are implemented correctly, the code modifications are minimal and appropriate, and the test cases cover all the bases.
Wow, that's seriously thorough. So MaintainBench isn't just about checking if the code still works after a change, but also about quantifying how much effort, how many modifications were needed to make it work.
Exactly. It allows for a more nuanced, dynamic assessment of maintainability by observing how the code adapts over time and measuring the cost of that adaptation in terms of code changes and structural similarity.
Okay, so MaintainBench puts the code through its paces when requirements evolve. Now let's talk about MaintainCoder itself. How does it actually generate code with maintainability as a core goal from the start?
MaintainCoder is designed as a multi-agent system. Imagine a team of specialized AI agents working together to build software.
Like a team of AI software developers. That sounds straight out of science fiction.
Right. Its structure is specifically designed to mimic the human software development lifecycle with a strong emphasis on principles that promote maintainability.
Okay, I like where this is going. So, how does this AI team operate?
It's organized into 2 main modules, the Code Framework module and the Code Generation module. The Code Framework module focuses on planning and architecture, transforming the initial requirements into a blueprint for maintainable software before any actual code is written. Then, the Code Generation module takes that blueprint and turns it into working code.
Okay, let's unpack that first module, the Code Framework module. Who are the key players on this AI architect team?
First up, we have the Requirements Analysis Agent. This agent's job is to dive deep into the software requirements, break down the problem into smaller chunks, and focus on what the user wants to achieve. It identifies core functions, highlights challenges, and proposes high-level solutions. But importantly, at this stage, no code is written.
So it's all about understanding the problem thoroughly, just like in the initial planning phase for human developers.
Absolutely. Then comes the Design Pattern Selection Agent. Think of this agent as the software architect. It's responsible for choosing the most appropriate design patterns for each part of the software. It considers the overall structure and how different modules will interact. The goal here is to choose patterns that promote modularity, reduce dependencies between different parts of the code, and enhance scalability and reusability.
And design patterns for our listeners are like tried and true templates for solving common software design challenges, right? They help create a good structure and make the code easier to understand and modify later on.
You got it. And this agent doesn't just pick a pattern randomly. It explains why it chose that specific pattern and even suggests alternative patterns and when they might be more suitable.
That's impressive. So, after selecting the right blueprints, who actually starts drawing up the plans for the software's structure?
That's the job of the Framework Design Agent. Based on the identified modules and chosen design patterns, this agent builds a preliminary structure for the software, defining the different classes, their attributes and methods, and clarifying how they relate to each other. The primary aim is to ensure each class has one specific job, a key principle in good software design that greatly improves maintainability. Again, just like with the Requirements Analysis Agent, no actual code is generated yet. It's all about design.
So it's like creating the skeleton of the software. What's the final step in this framework module?
The last agent in the Code Framework module is the Framework Evaluation Agent. It's the critical reviewer of the team. It examines the framework design for any potential issues, looking for areas where it could be improved in terms of clarity, scalability, performance, and adherence to best practices. It identifies potential problems with how tightly different parts of the code are connected, how well they work together, and suggests ways to optimize the design. This feedback then goes back to the Framework Design Agent for refinement in an iterative process.
So it's a continuous cycle of design and review, just like human architects would refine their blueprints before starting construction.
Precisely.
Okay, that's the planning phase covered. Now, how does the code generation module take these well-thought-out plans and turn them into actual functioning code?
The Code Generation module has two key players. First, there's the Code Generation Agent. This is where the actual Python code starts coming together. This agent takes the detailed framework design and converts it into functional code, focusing heavily on readability and maintainability. It includes clear comments, documentation, and follows standard Python coding guidelines. One important output here is a test interface function, which is crucial for the optimization phase.
So it's not just about spitting out code that works, but code that's easy for humans and maybe even other AI agents to understand and work with later on. What's the final step in this whole MaintainCoder process?
The last piece of the puzzle is the Code Optimization Agent. This agent's job is to refine the generated code to ensure it not only meets the functional requirements, but also performs well. It analyzes the original problem, the framework design, the generated code, and the test cases, looking for inefficiencies and areas for improvement. It executes the code, receives feedback, and makes adjustments until it's correct, efficient, and reliable.
It's like adding the finishing touches, making sure the code not only works correctly, but also performs well and meets all the necessary standards. It seems like MaintainCoder bakes in maintainability at every step of the way, from understanding the requirements to optimizing the final code. But the million-dollar question is, does it actually work? What did the experiments using MaintainBench reveal?
The results were pretty impressive. Using MaintainBench, the researchers found that MaintainCoder consistently outperformed the other AI models they tested against, including some powerful ones like GPT-4o and Claude 3.7 Sonnet. This was consistent across different levels of problem difficulty within MaintainBench.
And how did they specifically measure this improvement in maintainability?
They looked at both static and dynamic metrics. For dynamic metrics, which are at the heart of MaintainBench, MaintainCoder showed significant improvements in syntax tree similarity and code modification percentage when requirements changed. This means that when the code needed to be adapted, MaintainCoder's code required fewer and less extensive changes compared to the others. On average, they saw a remarkable 46.5% reduction in these adaptation costs.
Wow, that's a huge saving in terms of effort for future updates.
Wow.
What about traditional code quality metrics like maintainability index and cyclomatic complexity?
Interestingly, for simpler problems, MaintainCoder sometimes had a slightly lower maintainability index score.
Really, why is that?
The researchers believe this might be because MaintainCoder's more comprehensive design approach could add a bit of initial overhead, even if it makes the code more adaptable in the long run. However, it consistently scored lower on cyclomatic complexity, which indicates simpler, more maintainable code.
And what about those complex real-world scenarios?
That's where MaintainCoder really shined. On the harder mixture and competition-level problems in MaintainBench, it scored significantly higher on maintainability index and much lower on cyclomatic complexity compared to the other models. This suggests its structured, design-centric approach really pays off as the software gets more complex.
That makes sense. A well-designed architecture should provide more benefits as things get more intricate. Any other surprising findings?
Yeah, actually. They found that focusing on maintainability during code generation actually led to an improvement in the initial correctness of the code. MaintainCoder achieved, on average, 30.7% higher correctness on the original problems, simply because it generated more robust and well-structured programs from the get-go.
So, by aiming for code that's easier to maintain in the future, they accidentally made better code right from the start. That's a fantastic bonus. They also mentioned an ablation study in the paper. What did that show?
Yes. The ablation study was to figure out the individual contributions of different parts of MaintainCoder. They specifically looked at what happened when they removed the framework evaluation agent and the code optimization agent to see how much each contributed to the final results.
Interesting. So, what did they find?
They found that both agents had a positive impact on the correctness of the generated code, but the code optimization agent had a larger impact. This highlights the importance of that final refinement stage. However, they also noted that framework optimization is very cost-effective, usually needing only one round of design and review.
Okay, so MaintainCoder and MaintainBench seem like a significant leap forward. What are the broader implications of this research for AI-generated code, and what are some potential future directions you see emerging from this?
The researchers themselves highlight that this work provides a valuable benchmark for future research on maintainable code generation. MaintainBench gives us a standardized, rigorous way to evaluate how well different AI models can create code that can adapt to changing needs. This opens up a whole new avenue for research specifically focused on this critical aspect of software development.
So what's next in this area?
They suggest expanding MaintainBench to include even larger and more diverse types of problems to further test the effectiveness of approaches like MaintainCoder. They also mention exploring new code generation strategies and making improvements to the AI models themselves to further enhance code maintainability. This is a field that's ripe for further exploration.
So, to wrap things up, it sounds like MaintainCoder offers a promising new path for tackling the challenge of software maintainability in the era of AI-generated code. By incorporating proven software engineering principles like elements of the Waterfall model and design patterns, and by providing a dynamic and realistic way to assess code adaptability through MaintainBench, they're going beyond simply achieving initial functionality and focusing on building software that's truly designed to last and evolve gracefully over time.
Exactly. It's a fascinating glimpse into a future where AI can help us create software that's not only functional, but also robust, adaptable, and ultimately far easier and cheaper to maintain in the long run.
And for you, dear listener, who joined us today to learn and discover those aha moments, I leave you with this thought. As AI becomes more and more intertwined with how we build software, how might this fundamental shift towards maintainability reshape the technology we use every day? What new possibilities might emerge when the underlying code is inherently more flexible and less likely to break with every update? It's definitely something to ponder as we navigate this ever-changing digital landscape.